All right. Did I hit record? Yeah. Okay. All right. Let's get started. I was running a little behind this morning, but I got here at 8 o'clock right on time. Okay. So let's sort of recap logistics. So I checked with the TAs. They have graded. The homework's 3.1, 3.3. They're still working on 3.4 to 3.5. 3.6 is due today, and then I've assigned 3.7. I tried to pick a problem associated with 3.7 that wasn't too demanding given our topic today. And our topic today isn't, I don't want to say difficult, it's just it can be long because today what we're going to be looking is at equivalent systems in 3D. And I will tell you, because I'm sure that some of you are itching to get to this point, we're not there yet, but we are slowly nearing the place where our time in the land of 3 dimensions is at an end, okay? Because I know that 3D problems can tend to just make things a little more challenging. So this is going to be our last lecture in Module 3 in rigid body systems, and so this will be what we cover today is looking at 3D. In Module 4, we have 1 or 2 3D topics in there. Nothing particularly challenging, but again, they can be kind of long. But when we get into Module 5, Module 6, and Module 7, we're pretty much done with 3D. The only other time we discuss 3D is when we look at centers of gravity of volumes. But it is, I mean this when I say it, it is much easier than some of the topics we're doing now. Okay, so let's go ahead and get into the land of 3D. Oh, I just want to make sure I remind everybody once again about the Marshall Career Expo, which is taking place today. Again, there are a ton of companies there for engineering and STEM fields, so I would definitely check it out if you have time. Okay, the land of 3D. We actually have 2 example problems we're going to focus on today, but the first problem is really just meant to go through the process, and while it looks nasty, we'll actually be able to do that problem relatively quickly. The second problem I actually want to spend a little bit more time on because that one we need to write vectors for and so on and so forth. So just to make sure we're all on the same page, what we've done over the past few lectures is we have, I think, defined moments, and we have defined them, I think, till we're blue in the face. We've looked at the formal definition. We've looked at special cases with moments, such as force couples, moments about an arbitrary axis, moments in 2 dimensions. But in the end, I think we understand generally what a moment is. A moment is an action on a body that increases its tendency to rotate about a given point, and we compute the moment about that point by taking the cross product of R and F, R being the position vector that starts at the point in question and points to the line of action of the force that's causing rotation. What we got to last time was this concept of equivalent systems, the idea that 2 systems are statically equivalent, that if both the sum of the forces in the 2 systems are equal, as well as the sum of the moments in the 2 systems are equal. How did that concept go over? Did the homework make sense? Everybody okay with the concept so far? Okay, good. What we're going to do today is look at how this works in 3 dimensions. Now, I want to mention my disclaimer again, that right now we are not dealing with static equilibrium. Right now we're just adding forces up and adding moments up. We are not yet setting these sums of forces equal to 0. We will do that in the next module, where we then determine the unknown forces required to keep a rigid body in equilibrium. We have a name for those forces. We call those reactions. Probably not very inventive given the language in Newton's 3rd law. So what we're going to do today is we're going to do 2 problems. Okay, now I want to talk about the first problem real quick, because I'll tell you, it's going to look nastier than it really is. I'll just go ahead and pull it up in the notebook here. So here's the first problem. I have here a bracket that, didn't mean for that to happen. I have here this bracket in 3D that has a series of forces applied to it at various different angles. So we have a 1,000 Newton force, we have a 700 Newton force, and we have this 1,200 Newton force. And they're all at all sorts of different orientations and angles and whatnot. And I want to determine the moment, or the equivalent system, I should say, at point A. In other words, I want to take all these forces and replace them with a single force vector and a single moment vector. Now, what makes this problem, I would say, intimidating is probably this part right here, which is actually determining the force vectors and determining the position vectors. But I wanted to make the point today that what if I gave you those force vectors? What if I gave you those position vectors? Does the process become difficult? Okay, and hopefully after you see, the answer is no. Okay, in the last example, let's go to the last example and just make sure that we're clear on how that worked. Okay, so here was the last example, and we had this barge that was pushed by a series of boats, and we said, okay, let's take this barge with 4 forces and replace it with an equivalent system, a single force and a single moment. So how did we go about that? Okay, so the first step was we needed to write out each individual force in IJ notation. Okay, so here's force 1, force 2, force 3, force 4. And then the next thing we needed to do is write each position vector in IJ notation. So position 1, or position vector 1, position vector 2, etc. And then after that, it was pretty systematic, pretty rote. We just write down all our R vectors, write down all our F vectors, cross each R and F pair, sum the forces, sum the moments, we're done. And the point I wanted to make with this, this problem that we're doing right now is that doesn't get any more difficult if you're in the land of 3 dimensions. It doesn't make it any more challenging. It's the same process. Let's go through it. So I have here a series of vectors. So I mean, this is going to be really, really short. I just really want to make sure that this makes total sense. So we have, in this case, so we'll call it force. So we can go through and do this the same way, okay? So for this problem, we have 3 forces. We have 3 R vectors. These R vectors are going to be measured in meters, okay? And you can see here, because if you look at the schematic, all of the dimensions in the schematic are given in millimeters, but if you look at the position vector, you can see they've all been divided by 1,000, so they're in meters, okay? So we've got, let's see, 0.075I plus 0J plus 0.05K, 0.075I plus 0J minus 0.05K, and then 0.1I minus 0.1J plus 0K. Oop. Then just like last time, we have force vectors in newtons. So we have 300I minus 600J plus 200K. I'm skipping steps. 707I minus 0J, or plus 0J, I guess I should say, minus 707K. And then 600I plus 1039J plus 0K. Now, the only difference from what we did last time to what we would do this time is in this step right here, okay? Because last time what we did is we said, well, if we're dealing with a moment in 2D, we just have Rx Fy minus Ry Fx. But that's not going to work for 3D. For 3D, we're actually going to have to evaluate the cross product. So for each one of these rows, so for example, if I want, let's say, MB, it actually is going to be a vector this time. And so if I want to compute that vector, I'm going to have to take that crossed with that. So we would have to carry that out. So we'd have ijk, we'd have 0.075, 0.05, and then we'd have 300 minus 600, 200. And I would actually have to carry that cross product out, okay? But, I mean, I got to believe that by now that's not very difficult, right? I mean, it's long. I mean, you got to go through and do it, but you can do it, right? You can cross this vector, cross that vector, and so on and so forth. So just to make sure that we're all on the same page, when you cross this out, you'll end up getting the following. You'll end up getting 30i. You'll end up getting 0j, and you'll end up getting minus 45k when you cross that out. Now, the units for that are going to be in Newton meters because it's a moment. So I'm gonna take this and sort of move it down a little bit. So that's what we're going to get in this, in this entry, 30i plus 0j minus 45k. So I'm going to move this down a little bit. All right. So all you would do is you would just continue to do that for each row, and you would end up getting the following when it's all said and done. You'd end up getting, let's see, for this row, you'd get 0i. This one ends up being a little messier. This one ends up being, let's see, 17.68j, and this one ends up being 0k. And then so it had to happen so much. When I was in undergrad, we had a professor who had a cell phone song that was to the tune of Happy Birthday, and if anybody's phone rang, he'd be like, okay, it's your turn. I had a buddy of mine who, at the beginning of every class, would literally text the entire class and say, hey, your phone off, just to see if he could get somebody. And it was the last week of the semester, and somebody's phone rang. Everybody went, it's going to happen. All right. Tangent ended. Okay, so we would continue the same pattern here for the last one. And the last one, we would get 0i plus 0j. And this one ends up being 163.9k. Hopefully you can kind of see that, how that would work, especially with this last one. Because if you look at this last one actually is a moment in 2 dimensions, because we have a 0 component for k and a 0 component for k. So this one actually would work. We could do rxfy minus ryfx. But once we would get this, all we would then do is do what we did last time, and we would say, okay, let's sum these up. We don't care about this. This one, we do have to sum, and we got to carry that out. We end up getting like 1607i plus 439j minus 507k. And this one we'd have to sum out, and we end up getting, let's see, 30i. We get 17.68j. And then this one ends up being like 118.9k. So let me make that blue. So therefore, we can replace this system with a single force vector of this, and then a single moment vector of this. Let me move that over a little bit. See, this was a really, really short problem, and it probably looked like, if anybody snuck a peek at the slides before the lecture, it probably looked incredibly nasty. Okay. Really the point I want to make is that if you've got position vectors and if you've got force vectors, then the process of taking those vectors and collapsing them into a single equivalent force couple system of a single force and a single moment really should be very easy. Okay, and I hope it is. Is there anything about this that didn't make any sense? I know I did a lot of the math for you today, but in the end, I've got to believe that, you know, with enough time, you can take the cross product of this and this, this and this, and this and this. Okay, and to be clear, I'm well aware of the fact that on an exam you have very little time, so I know that. Let's just say I'm aware of that, and so the problems that I craft on the exam are taking that into account. Okay? So far, so good? All right, the problem I really want to spend some time on today, which I really want to make sure that we're a fan of, or you know, able to understand in 3 dimensions, is this one. Okay? This one, I think, is, for one, I think it's a little more representative of a real-world challenge. 2, if I'm being honest, it's a little near and dear to my heart as a civil engineer. And 3, I think that it's manageable. It's much more manageable than the last problem. We don't need to be given the position vectors and the force vectors. We could actually probably come up with these on our own and handle this one in class. Okay, so let's take a little bit of context here for this problem. So this problem, we have a square foundation that supports 4 column loads that are shown. And to be clear, this is a very real-world problem in the land of civil engineering. I think that engineers would absolutely love it if every single building that we constructed was just a box, but then the architects come in and say, that's boring. We don't like boxes. We need weird-looking buildings with curves and arcs that give the engineers headaches. I'm joking when I say that, but not really. I mean, in all honesty, boxes make our lives easier, but sometimes they don't serve the needs of the client. Okay, even just this building. Okay, I mean, there is a grid-like structure to this building, but it's not a perfect box. It's elongated. There's different wings of different sizes, and so it's not unheard of that you have column loads on a foundation that aren't simple. Okay, that aren't a nice little box. Okay. As much as we would like to deal with that, that may not be a real-world scenario. So we have a building that is going to be supported by a foundation. So does everybody know what I mean by a foundation? That's the substructure. That's everything below the ground that is keeping the building from collapsing. And it is subjected to a series of loads. So we have 40 kips, 8 kips, 12 kips, and 10 kips. Remember, a kip is a shorthand term for 1,000 pounds. So this is 40,000 pounds, 20,000 pounds, etc. If I'm being honest, in a lot of commercial building construction, these loads are actually pretty small. It is not that uncommon to design building columns for hundreds of thousands of pounds, maybe even bigger than that. That happens all the time. So should give you a little bit of an understanding of the magnitude of some forces that we deal with. What I want to do is I want to replace all of these forces with a single vector. The question is, where do I put that vector? That's the question. Okay, so that's going to be the challenge for the main crux of, or main bulk of our lecture today. Now, what makes this example nice is I think that we can form all of our force vectors by observation, and honestly, even a lot of our position vectors by observation as well. Now, in order to do this problem, what we're going to have to do is we're going to have to pick a point of reference, a point about which we can begin to sum moments. For the sake of discussion, I'm going to pick point 0, okay? So we're going to reference all of our position vectors from point naught, okay? So we'll say this is our point of interest. Okay? Now, before we get into the math, there is one final thing I want to say about this. As we get into this problem, some of you who are a little more astute in the land of statistics are probably going to look at this problem and look at the end result and ask, aren't we just computing a weighted average at the end of the day? And the answer to that is yes, okay? Basically, what we're going to be computing is a weighted average. We're going to compute the sum of the forces, and then where we locate that resultant is going to be a weighted average of the location of all of the other forces, okay? A simple terminology for you is if I have a rigid body and I wanted to idealize the weight of that rigid body at a single point, a weighted average for that region, we call that a centroid. So that's what's coming later, just to tie everything together. Okay, so what we're going to do here for this problem is we're going to sum moments about this point of interest. So what I'm going to need are 4 force vectors, and I'm going to need technically 4 position vectors. And so we'll look at that here in a second. So we'll just keep our notation simple for this problem. We'll call this vector RA. We'll call this vector R. Actually, since they're not, the A, B, and C are referencing the corners. So let's call this R20. Let's call this R8. Let's call this R12. Okay, just to keep things simple. All right. So let's start off with the position vectors, okay? And these are going to be in feet, okay? So I'm going to need your help with this one, okay? So help me out. So the position vectors here are, let's start off with R20, okay? If I want to go from point 0, bless you, to this point right here, how far along do I go in the x direction? How far along do I go in the y? 0. And how far along do I go in the z? 10. So this r vector right here is going to be, let's see, 4i plus 10k. Is that a fair statement? Now, associated with that, let's just make sure that we're clear on this. That associated force vector, how am I going to describe that associated force vector? How am I going to do that? Which component is that 20 going to be associated with? An I, a J, or a K? Say again. J. And is it positive or negative? Negative. So that force vector is just going to be negative 20J. Is that a fair statement?
Because it's moving down with the rest of the...
Exactly. It's moving down opposite the direction of the y-axis. All right, now let's keep going with this. So let's do R8. So R8, what do we got? So how far along do we go in the x-axis? 10. How far along do we go in the y? 0. And how about the z? For 8. For this 5. There we go. So 5. So we've got 10i plus 5j, and then we have F8 is negative 8j. So same thing with R12. So R12, that one should be pretty simple. What is R12 going to be? Just 10, 0, and 0, right? Just 10i, right? So 10i, and then F12 is minus 12j. Now, let's be clear about something, though, okay? Let's be clear about something. How many forces? Yes?
Shouldn't R8 be 5K? Yeah.
Sorry, what? Oh, you're right. You're 100% right. Yes. You are 100% right. I'm sorry. 0.125 on the mistake counter for that one. That was a good one. Again, we will never hit 7 on the mistake counter because it's a corrupt system, because I'm the one who challenges it. So I might lose count of how many mistakes we are at so far. I know we're at 1 for the typo on the exam solution. So I think with all the mistakes now, we're at like 0.6. Joke. I know. Okay. All right. So I want to be clear. There are 4 forces on this system. Okay. There's a 20, an 8, a 12, but then there's a 40. Okay. So we've got a force vector 40, which is minus 40j. But I guess my question, what is the position vector associated with that force? Say it. 0. There is no vector associated with that force. So what, if I was being a stickler in terms of my notation, I would just say a 0 vector. But what does that mean? Okay. So let's go back to the original schematic. The 40 kip load goes directly through the origin, goes directly through point naught, right? Okay. When we originally started the concept of moments, when we originally started looking at that, we said that moments are addressing a problem with static equilibrium that forces can't handle on their own, and that is that moments represent an action on a body that increases its tendency to rotate. So my question for you is that if that 40 kips is going directly through point naught, is it going to want to rotate point naught? No, it's not, right? I'm saying not all over again. That 40 kip load will generate 0 rotation at the origin. Okay? That doesn't mean the other forces won't generate rotation or want to generate rotation. Of course they will, but that one won't. So when we do R cross F for this pair, it's going to be 0. But that makes sense because it's going right through the point in question. Everybody okay with that? Okay. So now what we're going to do is we're going to evaluate all of our cross products. Okay. So and I'll say, for some reason on this one, I didn't do this in a table like I did last time, but that doesn't really matter. So let's evaluate the first one out by hand. So let's handle it like this. So M20 is going to be R20, bless you, crossed with F20. So let's do this one by hand. So I, J, K. So the R is going to be 4, 0, 10. And then the F is going to be 0, minus 20, 0. Is that a fair statement? So what do we have? We have I, a determinant, minus J, a determinant, plus K, a determinant. Okay. And so what do we get inside the I? We get 0, 10, negative 20, 0. Inside the J, we get 4, 10, 0, 0. And inside the K, 4, 0, 0, minus 20. So inside the I vector, so 0, minus 200, so minus negative 200, so that's going to be 200. Minus J, that one's going to be 0, plus K negative 80. 200I minus 80K. I did that right? I think I did. So that's that one. And so now we just continue it on for the others, okay? And they're going to be just as easy, I think, to deal with. So M8 is going to be R8 crossed with F8. So that's going to be 10I plus 5K crossed with negative 8J. And hopefully I think by now that you can trust me on what the answer ends up being. And I end up getting 40I minus 80K. Is that okay if I just give you the answer, or do you want to go through it? Okay, I feel like everybody's okay with that. I'm going to scroll down a little bit and write 8 better than that. Okay, so M12, so we're going to take R12 cross with F12. This one's going to be a lot more basic because all we're going to have is 10I crossed with negative 12J. And when you chug this one out, you just get minus 120K. But what's M40 going to be? 0. So it's going to be R40 crossed with F40, but that's going to be 0. So, if I wanted to replace this with an equivalent force couple, what I would do is I would say, okay, R, my resultant force vector, is just the sum of the individual forces. But what is that? So what did we have? We had 40, 12, 8, and 20. So let's see, 12 and 8 is 20, 40. I think that's 80. Did I get that right? I think that's right. And that's in kips. And then our resultant moment vector is just summing all of these up. So let's sum up the I components. So the I components, what do we have here? So 240, we get 240I minus 280K. And that's in foot kips. But we're not done with this problem. We got a little bit more we're going to do with it. This part's kind of cool. But let's just make sure we're clear on this. So for the I component, we had that and that, so 240. And for the K component, that, and that. So maybe I'll highlight these so you can see what I'm adding. So I'm adding this, and this. And I guess this if I wanted to be technical, although we all know that's going to be 0. All right, before I move on, because this next part's going to be a little different, but before I move on, is everybody okay with this? Any questions? Yes?
So the resultant force is negative 80.
Yes.
But you said if we were going to find the force couple, so would that mean that would be negative 80 going this way and that way?
Oh, I understand. So that probably that notation is not the best. So when we're saying equivalent force couple system, what we're basically saying is this and this. So that yeah.
Couple.
Yeah, so I'm using the term couple and moment interchangeably here. Honestly, probably not the best notation or best terminology. It matches what the textbook's using. So I would have no problem if you said equivalent force moment system. So, you had a question? Oh. Okay. Everybody good? All right. Now we're going to do something a little unique, okay? Because I want to go back to an original question I had, and please forgive my artwork, okay? What I want to do is I want to deal with simple systems as much as possible. So let's go back to that slab. So here's the slab. All right, so I'll put some three-dimensionality on it. Okay, and we had a coordinate system where we said that was X, or no, sorry. That was Z, that was Y, and that was X. Okay, so this was the slab that we were given at the beginning of the problem. And at the beginning of the problem, we had 4 forces on the slab, right? Okay, I want to replace that with a single force, okay? Now, let's put that force right there. I don't know. Now, I want to replace that with a single force, and I want to replace it such that it is statically equivalent. So what that means is that this force system has to have the same sum of forces and sum of moments as that force system, okay? So let's talk about sum of forces. If I want to replace those 4 vectors with just one, what does the magnitude of this vector have to be? Well, better be negative 80, right? Because that's the magnitude of the forces on the original system. So this better be minus 80 kicks. But that's not enough. What I really need to know is where do I put it, okay? Well, let's see if we can figure that out. So let's determine some position vector R. Okay, let's see if we can figure that out. So R, let's call it this. I don't know what those values are yet. We'll figure that out. But I want to figure out where to put that 80 kip load so that it is statically equivalent to all of the other forces, right? And so what I'm saying is that this dimension here is Rx, or sorry, no, I got that backwards. This is Rx, this dimension Rz along that axis. I want to figure out where to put that thing. Now the force vector, the actual magnitude of the force, is 0I minus 80J plus 0K. Now, in order for this system to be statically equivalent, both the sum of the forces and the sum of the moments must be identical. So maybe what I ought to do is compute the moment of this system. And how do I do that? I take R cross with R. Let's do that. Let's see what happens here. So we have the I component. So the J component. and the K component. You see what I did? Just knock out the row and column, write them out. Let's carry this out. Let's see what happens. So 0, 0, negative 80 RZ, so that's 80 RZ minus J. That's going to be 0 and 0. That's going to be 0. I can save myself some room there. That's going to be minus 80 Rx. So therefore, R cross R is 80 RZI minus, or, let's just do plus negative 80 RX K. So wherever I place that load on this foundation mat, that's going to be the moment it generates. But what must that moment equal? Well, I propose that moment must equal the moment in the system. And we already determined the moment in the system. That was 240I minus 280K. Didn't we already do that? So maybe what I ought to do is I should say, therefore, 80 RZ is 240. So RZ is 3, in this case 3 feet. And negative 80 RX is negative 280. Or RX is, what is that? 3.5? 3.5? So what I can do is I can say, here's my foundation mat. Instead of all those loads, just 80 kips, and place it such that this dimension is 3.5 feet, and that dimension is 3 feet, and that system is statically equivalent to the last one. Does that make sense? And what I would tell you is that if all that we are considering are these 4 forces, then the coordinates of this point, this 3.5, 0, 3, we have a name for that point. We call it the centroid. That is the centroid of that group of loads. And some of you might ask, isn't this just a weighted average of where those points are? You are 100% right. There are very strong analogies between centroids and weighted averages. And we will learn that when we start getting down into that land. Does that make sense? So the 3D problems that I'm trying to give you on homeworks and exams, I promise, they're trying to be more like this than the last problem. The last problem I don't think is conceptually any more difficult than this one. It's just longer. And I'm trying to make them as managed as possible from a time consideration. Does that make sense? All right, does anybody have any questions? All right, I was running a little late this morning, so I'm going to pay it forward a little bit. I'm going to pull up the code again today, but I'm not going to count anybody late today. That's all I've got, everybody. I will see you all on Friday.